In this lecture, we will see the basic principle and applications of laser. Uh, First, let's see the basic principle of laser. When excited atoms return to their lower energy states, light photons are emitted. The spontaneous emission of radiation is the name for this phenomenon. This spontaneous emission has been used to explain all of the processes of light generation. On the other hand, Einstein proposed that there was another mechanism for the production of the light. The term for this was stimulated emission of radiation. Lyman was the first to successfully generate visible light using stimulated emission of radiation in 1960. The laser was the name given to this light source, which stands for light amplification by stimulated emission of radiation. The atomic system interacts with its surrounding through the absorption of radiation by the atom or the emission of its energy to the radiation. Atoms move from one energy level to another during this process. The interaction between atoms at two energy levels and the surrounding radiation is seen in the figure. This figure. As shown in the figure, there are three types of interactions: absorption, spontaneous emission, and stimulated emission. Atoms in the ground state E1 observe the energy of the radiation and transition to the excited state E2 during the absorption process. So atoms in ground state observe the energy from background radiation and move to the excited state. This process is called absorption. In the spontaneous emission process, atoms at E2 return to the ground state E1 by emitting energy in the form of photons to the radiation. So in the spontaneous emission process, atoms in the excited states spontaneously move to the ground state, emitting photons. The energy of the emitted light photon is equal to the difference between two energy levels in this case. The generation of light by gas discharge is a typical example of a spontaneous emission of radiation. In the stimulated emission process, atoms in the excited state observe energy from the background radiation and move to the ground state by emitting two photons. So there are three ways that atoms interact with their surroundings: absorption, spontaneous emission, and stimulated emission. The two-level atoms transition between them by either emitting or observing photons. Stimulated emission occurs when excited atoms are stimulated by an external photon. The energy difference between two energy levels in this case should be the same as the energy of a stimulating photon. So the stimulating photon's energy should be the same as the energy difference between two energy levels. The main distinction between spontaneous and stimulated emission is that stimulated emission emits two photons, whereas the spontaneous emission emits only one photon. Furthermore, the physical properties of the two photons emitted in the stimulated emission are identical. Twin photons are the name for these photons. The frequency, amplitude, direction, and the phase of these two twin photons are all the same. To put it another way, they are entirely coherent. These coherent lines constructively interfere with one another. The laser activity requires this stimulated emission process. The laser light can transmit a long distance without spreading out due to these properties of the light emitted by stimulated emission. The light emitted by a gas discharge, which is due to the spontaneous emission, on the other hand, spreads out and consequently does not move a long distance. This is due to the fact that each atom's light photons are emitted in different directions and have different phases. So this figure shows the photons emitted by spontaneous emission. The photons have all different directions and their phases are different. This figure shows the photons emitted by stimulated emission. Twin photons here has the same frequency, phase, and the direction. The stimulated emission process causes the twin photons to be released. All of the physical characteristics of two photons, including frequency, amplitude, direction, and phase, are the same. The ratio of stimulated to spontaneous emission will be calculated below by taking into account the change in number of atoms in the excited state E2 as a result of three processes. Let's start by looking at the increase in the number of atoms in E2 as a result of absorption process. The atoms in E1 absorb energy from the radiation and move to E2. In this absorption process, the number of atoms moving from E1 to E2 is proportional to the number of atoms in E1 and the energy density of radiation. As a result, the absorption process changes the number of atoms in E2 as follows, given by this equation. Here, N1, N2, and rho mu are respectively the number of atoms in E1 and E2 and the energy density of radiation. The proportionality constant of E21 is the Einstein coefficient of absorption, which depends on the material property. Second, the number of atoms in E2 is reduced in the spontaneous emission process as atoms in E2 move to E1. The number of atoms that move from E2 to E1 is proportional to the number of atoms in E2. Thus, the spontaneous emission process results in a change in the number of atoms in E2 as follows. This relationship here, A to 1 is called the Einstein coefficient of spontaneous emission. Third, in the student emission process, the number of atoms in E2 decreases as they move to E1. The number of atoms that move from E2 to E1 is proportional to the number of atoms in E2 and also the radiation's energy density. As a result, the change in the number of atoms in E2 as a result of the student emission process can be calculated as follows. So this relationship here, B21 is called the Einstein coefficient of student emission. The number of atoms in E2 does not change if the system of atoms and radiation reaches thermal equilibrium at temperature T. That is, condition dN2 of dt equals 0 has been met in the thermal equilibrium condition. By adding the changes in the number of atoms in E2 caused by three processes, we arrive at the following relationship. So we add up the change of atoms in the excited state by three processes. This one. So spontaneous emission and stored emission and absorption. So to satisfy the equilibrium condition, this change of number in the excited state should be 0 at the thermal equilibrium. When we rewrite the Bower equation for the radiation density rho mu, we get this relationship here, 1 over N1 over N2 can be written by the Boltzmann distribution. So this can be replaced by this Boltzmann distribution. So the ratio of numbers in excited state to the number in the ground state is the exponential of the energy difference over kT thermal energy. And the energy difference represents the photon energy h mu. So in the thermal equilibrium between atom systems and surrounding radiation, the radiation energy is represented by this equation. When radiation with frequency mu is in thermal equilibrium with atoms with energy levels E1 and E2 at temperature of T, the above equation is used to calculate the radiation energy density. The radiation density expression obtained in the previous slide must be the same as the black body radiation density, which is given by this equation. When we compare two equations, we can get these two relationships. The coefficients of absorption and stimulus emission are the same according to the first equation. So B12 is the coefficient of absorption, and B21 is the coefficient of stimulus emission. So these two coefficients are the same. And second equation tells that the ratio of spontaneous emission coefficient to the stimulus emission coefficient is given by these values. The ratio of spontaneous to stimulus emission is given by this equation. The rate of spontaneous emission is proportional to the coefficient of spontaneous emission, rate 1, but the rate of stimulus emission is proportional to both coefficient of stimulus emission and the radiation density. In the stimulus emission process, we need the stimulating photons from radiation background. So the rate of the stimulus emission is also proportional to the radiation density of background. And this radiation density is given by this equation, so we can put that here. And the ratio of two coefficients is given by this relationship, so we can put that here. Then this term is cancelled out, so we can have this equation. The stimulus emission is insignificant in comparison to spontaneous emission for H mu is much larger than the thermal energy. So this means that the temperature is very low, it's low temperature case. In the case of low temperature, this exponential is very large, so the value of right hand side in this equation is very large. That means that the denominator of the left hand side should be small. So the stimulus emission becomes insignificant at the low temperature case. On the other hand, in the case of KT is much larger than H mu, so high temperature case, the exponential value is very small. So that means that the numerator in the left hand side should be very large. So in that case, the stimulus emission prevails. So in the low temperature case, the stimulus emission is insignificant. However, in high temperature case, the stimulus emission prevails. the temperature at which the rate of the solid emission is equal to the rate of spontaneous emission can be obtained by setting this equation to 1. So if the value of the right hand side becomes 1, then the rate of spontaneous emission become the same as that of the solid emission. So if temperature is determined to be 30,000 Kelvin for the wavelength of 600 nanometer, the light produced by solid emission is therefore not available to us under normal conditions. However, the population inversion makes the solid emission dominant. In a population inversion, there are a lot more atoms in the excited state than there are in the ground state. If the population inversion is achieved, atoms in the excited state have a very good chance of undergoing a solid emission transition to the ground state. However, for stable laser action, these population inversion requirements must constantly be met. Otherwise, the laser action comes to a halt, since the solid emission is impossible to achieve without population inversion. As a result, for stable laser action, the population inversion should be maintained always. Once a pair of photons are emitted by the solid emission, an avalanche of solid emission happens if population inversion always occurs. Finally, the solid emission emits all of the light photons. For stable population inversion, a metastable state is required. The metastable state has substantially longer lifetime than the usual energy state. We will see how this metastable state enables laser action further below. Now let's calculate the population ratio of atoms in two energy levels whose energy difference corresponds to yellow light at 300 Kelvin. Using the Boltzmann distribution, we already saw this. The ratio of number of atoms in excited state to that in the ground state is given by Boltzmann distribution. E2 minus E1 is the difference between two energy states, and KT is the thermal energy. And here we have the yellow light. So the energy difference between two energy levels is calculated as this relationship. So yellow light has the wavelength of 550 nanometer, so we can get this value. And the thermal energy, temperature is 300 Kelvin, so K is Boltzmann constant, so we can get this value. If we put this E2 minus E1 here, and thermal energy here, we can finally get the ratio of number of atoms in the two energy states is given by 10 to the minus 40. So the number of atoms in the excited state is very small compared to the number of atoms in the ground state. So as a result, compared to the ground state, the number of atoms in the excited state is extremely small. Now let's see the laser action process. 3-level and 4-level lasers are the two types of lasers that can be used. We will go over the laser action process for level laser. Since this laser process involves 4 energy levels, we call it 4-level laser. The laser action process for a 4-level laser is depicted in the figure, this figure. The laser action is divided into 4 steps: pumping, fast radiation-less cross transition, light amplification, and decaying are the steps involved. In step 1, laser medium is given the appropriate energy to excite atoms from the ground level to the pump level. Pumping is the term for this step. The atoms in the ground level absorb the energy from outside and move to the excited levels, which is called pump level. So this process is called pumping. A very fast decay, typically radiation-less, from the pump level to the upper laser level is the second step of laser operation. The upper laser level is unique in that it has a very long lifetime, while the most of excited levels in an atom have a lifetime of 10 to the minus 8 seconds. The upper laser level has a lifetime of 10 to the minus 3 seconds. So upper laser level has lifetimes about 10 to the 5 times more than that in the ordinary excited states. As a result, we refer to the upper laser level as metastable. So this upper laser level is a metastable state. So its lifetime is 10 to the minus 5, which is 10 to the 5 times more than that of ordinary excited states. So pump level is also the ordinary excited state, so its lifetime is just 10 to the minus 8 seconds. So once the atoms move to this pump level by external energy, the atoms immediately drop to the upper laser level, because the pump level is ordinary excited state, and this lifetime is just 10 to the minus 8 seconds. So the atoms here in pump level instantly move to the upper laser levels. Then atoms pile up in the metastable state as they rapidly drop from the pump level to the upper laser level. Atoms at the lower laser level, on the other hand, decay rapidly to the ground state, since this lower laser level is an ordinary level with a lifetime of 10 to the minus 8 seconds. The lower laser level is also ordinary excited state, and its lifetime is just 10 to the minus 8 seconds. So atoms moved to this lower laser level immediately decay to the ground state, since the lifetime of this lower laser level is just 10 to the minus 8 seconds. Therefore, the population inversion is formed, as a result of the lifetime difference between the upper and lower laser levels, and this situation is always maintained between these two energy levels. So the population inverse between upper laser level and lower laser level is maintained always. So laser action is possible between these two energy levels. So that means that stimulated emission is possible between these two energy levels. And since the population inversion is always maintained between these two levels. The light amplification process by stimulated emission is the third step in laser operation. A light photon from an atom's spontaneous emission causes a neighboring atom's stimulated emission. Following that, since the population inversion between the upper and lower laser levels is always maintained, an avalanche of photons are produced via stimulated emission. Eventually, only stimulated emission produces all of the light photons. Atoms quickly return to their ground state after finishing the light amplification process and are ready to be excited by pumping energy sources. These four steps of the laser action process repeats cyclically, resulting in stable laser light generation. Depending on the laser medium, the types of energy used in the pumping process vary. Optical energy is used in the majority of solid and liquid lasers. On the other hand, electrical energy is suited for gas or semiconductor lasers. Since gas has a sharp pump energy level, optical energy is not suitable for pumping gas atoms. Instead, an accurate energy matching the difference between the ground and the pump levels should be provided for pumping. So, for gas or semiconductor lasers, the electrical energy is more suitable for pumping. However, due to the interactions between lasing atoms and their surroundings, the pump level of the lasing atoms in the solid or liquid laser medium is generally broadened. So energy levels are broadened due to the interaction between lasing atoms and their surroundings in the solid or liquid. So in this case, the broader frequency bandwidth optical energy is adequate to excite lasing atom to their broad pump level. As generated light photon from an atom passes through the laser medium, it induces neighboring atoms to generate light photons through stimulated emission, and this process continues all the way to the other end. So through the laser medium or to the other end. For one complete passage of light photons across the laser medium, the gain in light photons due to stimulated emission is less than 5%. So a feedback system is employed to increase this small gain. As shown in the figure below, the feedback system consists of two refracting mirrors. A mirror's refractivity on the left-hand side is 100%. On the other hand, To release the output of laser light via it, we employ a 95 to 99% refractivity mirror on the right-hand side. Since the light emitted by atoms is refracted back and forth by mirrors, all of the light emitted is generated entirely by strobed emission. The figure depicts this process schematically. The rate of strobed emission during the raging process was increased by the resonance cavity system with the two end mirrors. So eventually, all photons are produced by strobed emission. As seen in the figure below, a laser can be divided into three main components: the pumping energy source, the laser medium, and the feedback system are the three components. A cavity or resonate is a common name for the feedback system. So the main components for laser is laser medium and the pumping energy and the refracting mirror. So this resonator system. The laser is made up of three basic parts: the laser material, the pumping energy, and the resonator. The laser medium can exist in any state, including solid, liquid, and gas. Depending on the laser medium, a variety of energies, including optical, electrical, chemical, and so on, are employed as the pumping energy. Two refracting mirrors make up the resonator, which boosts the rate of strobed emission as light bounces back and forth between the mirrors. Refractive coatings are typically applied to laser mediums and two ends in solid and laser medium. So refracting mirrors are coated on both ends of the solid laser medium.